I'm sorry. Well, remember you guys had a little bit of a break on assignments. Yeah, at one point, I think you only had like one assignment due. And didn't you enjoy that?
Oh, for this class?
Yeah. Oh yeah, I don't, the other classes don't concern me. They concern you. All right. On the plus side, assignment 9 is the last assignment, I promise. I want you, so like I was saying, I want you to work in groups for assignment 9, just because it is kind of problem solving and it'll help to be able to talk it out with someone. And so obviously if you're working as a group, then just submit it as a group, okay? Because you will want to talk it through with someone, okay? So assignment number 9 is the last assignment. Woohoo. It's good to know. Yeah. It's actually on the assignment. It's always on the assignment. Dude, December 3rd.
It's usually a good crack period afterwards. And then regain some footing.
So this one is due December 3rd, our last class. You should work in groups, especially for assignment 9. Especially for assignment 9. And of course, if you're working together, submit as a group. Okay. Same thing goes for assignment 8, but assignment 8 is, I'd say, very reasonable, and so you can kind of handle it if you're working on your own and you don't want to coordinate with anyone, that's fine. I don't care. But then assignment 9, you'll want to kind of talk it out. Okay. Any housekeeping questions before we start? No. All right. So today we're starting chapter 12. We're only doing 12 sections in chapter 12. No, we're only doing 2 sections in chapter 12. And so we're going to do the sine laws today, and then we're going to do the cosine laws next day. And what you'll see is that they're very similar, right? And they're just tools. So we've got SOHCAHTOA for right angles, right? So now we're broadening the horizons, and so now we don't need to have right angles anymore, but that's the only difference, right? We're going to be able to solve for all the angles in there, in a triangle, in any triangle, and we'll be able to solve for the lengths of all the sides. So this is chapter 12, Geometric Applications of Trigonometry. Section 12.1 is the law of sines. Depending on the information that we're given, right? And so I'll have to give you 3 pieces of information, and then from those 3 pieces, whether those are an angle and 2 sides, or 2 angles, 1 side, whatever, you'll be able to solve for the rest of the angles and sides, right? And so that's what we're doing in this section. The law of sines is going to apply to if we have some information, and then you have to use the law of cosines for if you're given other pieces of information. And we'll talk about that, obviously. So in this section and the next, we will develop tools for solving oblique triangles. Oblique triangles are just, there are no right angles in there. So no 90 degree angles. We will develop tools for solving oblique which just means no right angles, triangles. Just as before, we're still going to use Greek letters for our angles, and then what we'll do is we'll use the English alphabet lowercase letters, kind of the equivalent for the lengths of the sides. So we use Greek letters to denote angles. And of course, they're measures, but that's kind of understood. And the corresponding English letters, it's the Latin alphabet, right? Our alphabet, I think. Anyways, we'll just say English letters. To denote the length of the side opposite that angle. Of the side opposite that angle. Whoops. In a triangle, we're going to have three angles, triangle. So we're going to use alpha, beta, and gamma.
I'll just click here. Triangle.
Well, I know. There is some logic in there after all. Triangles. Anyways, here we go. Yeah. It's good to have an appreciative audience here. So we're going to use alpha, beta, and gamma. Gamma is actually the C. Anyways, not to get into it, but I guess I did look it up though. Gamma means camel in Greek, and so the gamma symbol looks like a camel's head, and I guess they don't distinguish between G and K like we do. Anyways, and so gamma is C. And so so we've got alpha, we've got beta, and then gamma kind of looks like, well, I don't do a very good job of drawing it. It looks like this, but usually mine end up looking like that for some reason. So just, I don't know. Just sloppy, I think. So should look like this, like the first one, but I don't know. And so these are the angles that we'll have. And then the sides, of course, that are opposite those, we use the lowercase letters. Oh, I should say, and the corresponding English lowercase letters, A, B, and C. So if you've got a triangle, any triangle now, we can handle. Mine always kind of end up looking the same. We usually denote A, B, C, right? We can label the or the points of the triangle, right? And so this would be triangle ABC. But then, of course, we've got alpha, and then the side opposite that is going to have length A. We've got beta. The side opposite that is going to have length B, and then we've got gamma. Let's see if I can do a proper one here, sort of. And on the opposite side, we've got C. So given 3 of these, angles and sides, kind of a mixed bag, we'll be able to use either the law of sines or later the law of cosines, we'll see, to solve for the rest of these angles. And then we'll also have a formula for calculating the area of any triangle, right, depending on the information that we have. You have probably been told this before, right? If not, maybe by me. You should always just use the information that you've been given in the problem, right? So as much as you can, use given information, not information that you've solved for, right? Because if you've solved for it, there might be an error in that, and then that's gonna kind of cascade down through the rest of your answers, right? So as much as possible, you're gonna wanna use information that was given to you in the problem. So as a rule, whenever possible, I'll put in brackets here, whenever possible, because sometimes it's not possible to use information that we've been given, but whenever it's possible, we should solve for quantities. We should solve for quantities using the original data. We should solve for quantities using the original data given in the problem. This reduces the risk of errors. And that's a good rule for anytime you're solving for anything, right? Not just this. So like I said, the law of sines applies to some cases, right? And so I'll have to preface it with, in certain cases, we can use the law of sines to solve oblique angles. And you've got the law of sines on your handout. So in certain cases, we can use the law of sines to solve oblique triangles. And I'm going to go grab theorem 12.1. So here, the law of sines says that, okay, if we're given a triangle with angle side opposite pairs, and so those are just the alpha A, beta B, gamma C, right? And so those are just angle side opposite pairs, then just as a fact, these ratios are going to hold, right? So the sine of alpha over A, right? So the sine of the angle over the length of the opposite side is going to be the sine of the angle over its opposite side, which is going to be equal to the sine of the angle over its opposite side, right? So for all three angles. Of course, we can just take the reciprocal and it's going to be equivalent, right? We just flip all these upside down. So depending on how you prefer to look at these, but I mean, I'm just going to stick to this one. You don't actually need this one because they're, I don't know, this is just the reciprocal of that, right? So I'm just going to focus on this one here. And so, like I said, in certain cases, the key being that we have to have at least one of these pairs, right? Otherwise, it's going to be really hard to solve for these. So, so like I said, in order to use the law of sines to solve a triangle, we need at least one angle side opposite pair, right? So we need at least one pair. And then because I said I give you three things, right? The other thing is just going to be something from another pair, right? And then that'll help you solve for the rest. So in order to use the law of sines to solve a triangle, we need at least one angle side opposite pair. So at least one of alpha A, beta B, or gamma C. All right, those are your angle side opposite pairs. Okay. Let's do an example. Solve and give the exact answer and the approximate answer, or the approximation rounded to hundredths, so that's 2 decimal places, and sketch the triangle. Solve and give the exact answer and the approximation rounded to hundredths and sketch the triangle. If I give you alpha is 120 degrees, you'll be pleased to know that we're working in degrees and not radians now. Which means you have to change to degree mode, right? But besides that, we're home free. A is 7 and beta is 45 degrees. Oops. We have an angle side opposite pair, right? Alpha and A, and then we have beta. And so if we're looking at, so we know that the sine of alpha over A is the sine of beta over B, which is the sine of gamma over C. So if I know alpha and A and beta, well, then kind of the natural next step to solve for would be to solve for B. Right? So we have everything to solve for B. Right. Because if we break this down to just sine alpha over A is sine of beta over B, right? We don't need to have that sine gamma over C hanging around. We can kind of focus on whichever section we want. So then that means that we have the sine of 120 degrees over 7 is the sine of 45 degrees over B. Compared to what you have been solving for, this is not that bad at all, right? You're going to solve for B, so you're going to cross multiply B over, and then just kind of switcheroo things, right? And so you're going to get that B, right? I'll do it once. How about once properly, and that's it. B times the sine of 120 degrees is 7 times the sine of 45 degrees. So B is going to be 7 times the sine of 45 degrees over the sine of 120 degrees. Now, as long as you're in degree mode, right, your calculator, and so you shift setup, angle input, and then you want to be in degree mode. As long as you're in degree mode, your calculator gives you the exact answer. So we can do 7 times the sine of 45 divided by the sine of 120. So the exact answer is 7√6 over 3. Does your calculator give you the exact answers? Yeah.
I mean, we want the fraction there.
Yeah, so this is the exact answer, right? And so I asked for the exact answer and the approximation, rounded to hundredths. And so for the approximation, it's approximately equal to 5.72. Right. I've got one of those to lend you if you want. Not now, but later.
Like normal mode, you get square root, and then I have to switch it into like stat mode to get the decimal.
Really?
Yeah. Or I mean, there might be. An
Oh,
easier
that's
way,
so
but I
annoying.
just don't know how.
Oh, is that, what brand is that? Is that Sharp?
I had one when we started class. And I can do it. It's just the extra step. I have to go back and read the whole thing.
Well, yeah, for this step especially, like that one is the easier. I've got some extras that you can borrow.
How do you switch between the
Use the S to D button. It's like a,
Okay.
see it? It just switches between. Okay, so that's one down. So now we know alpha, we know A, we know beta, we know B. So now we can move on to gamma, right? We know that these angles still have to add to 180. So finding gamma is probably the easiest thing. And then we'll be able to find for C, or solve for C. So we can find that gamma. Oh, does it give you the exact answer?
It's not the exact.
Does it give you the 7√6/3? Yeah? Awesome. We can find gamma is 180 degrees minus 120 degrees minus 45 degrees. So gamma then is 15 degrees. Tiny angle. Remembering that we want to use as much of the given information as possible, right? And so I'm going to use the sine of alpha over A is the sine of gamma over C, right? Just because it uses alpha and A. And so now the sine. That happens actually. So,
I'm so glad you asked, Josh. I woke up at 6.
Isn't that late for you? Yeah. So we've got the sine of 120 over 7 is the sine of 15, over C. Doing my switcheroo here, I'm not going to show my work anymore. C, right, is going to be 7 times the sine of 15 over the sine of 120. And the exact answer that I got was -7√6 plus 21√2 over 6. But that's just because the calculator gives it to me, not. Does it not give it to you? Oh. Is it still over 6? Or is it over 12 maybe? Are you guys maybe I did something. Okay. Yeah. So then C, did it work out, Jackson? Okay, good. So then C is approximately 2.09. All right. So now if we have to, so now we have all these pieces, right? If we had to sketch this triangle, I don't want you to spend a lot of time. I know you guys probably have like protractors and stuff. No? Okay. I taught the math for the mechanical engineering and they were I'm like, just sketch it. Just rough ideas here. But they brought out their protractors and they're measuring. Okay.
How about our assignments? They have to be exact.
No.
So I can just do like a triangle and then just put in whatever you
Yeah.
want. As long as like it has to be
Yeah.
scalable.
Let's pretend that we're but yeah, honestly, I mean, if you did something like this and you told me that this one's 15 and this one's 7, or what is it, 45, well, it doesn't really work because this one's 120, but I mean, the idea is the same.
That's not shit. Like, you don't want to see that, or it's fine.
Ideally, because the 120 doesn't really make sense in that case, right? You'd probably put a stop to that and say, oh, I need to open this up a little bit. have something like this. But really just sketch this stuff. I'm not even sure I made you do it on the, let me see. No, I don't make you sketch anything on the assignment, which means I'm not going to make you sketch anything on the test. So you will need to sketch stuff out for those word problems, otherwise they're really hard to solve. Very, very hard. But because we're working with bearings, and we'll get there, it's not going to be as, I don't know, kind of arbitrary. So if we need to have an angle that is 120 degrees, what I'm going to do is I'm going to accommodate that by drawing something like this. So here I've got alpha is 120 degrees. Like I said, is one of these angles 45 and the other 15? No, not really, right? So that's broad strokes here. So we're going to let this one be the beta, which is 45 degrees, and this one will let be the gamma, which is, oops, need to make room, 15 degrees. Opposite alpha, we've got A, which is equal to 7, right? Because that was given. Opposite beta, we've got B, which is approximately equal to 5.72. And then opposite gamma, we've got C, which is approximately equal to 2.09. You're welcome to use the approximations. I mean, ideally, we would use the exact answers to kind of figure these things out. But you're okay to use, bless you, to just use the approximations. Okay. Okay. We're going to be classifying angles. This isn't really a big deal. It's just so you have it in case, you know, I make a reference to an angle side triangle, for example. And so we can classify triangles by the information that we're given. By the information we are given. For example, an angle side. Angle side. The given side, so we'll only have one side that we're given and two angles, right? That's what we had just now, right? Potentially. Is where the given side is adjacent to just one of the angles. The given side is adjacent to just one of the angles. We can have an angle side angle. And like I said, I don't want you to commit these to memory or anything, but it's more about, okay, well, the ones that we're talking about now we'll be able to use with the, to solve with the sine laws, and the other ones we'll be able to solve with the cosine laws. And so that's why I want to just talk about it, but it's basically, depending on the information that you have, regardless of how we classify these triangles, you're going to be able to figure out if you can use the sine laws or if you have to use the cosine laws. So the angle side angle is the given side is adjacent to both the angles, right? And so if you're reading these, right, AS, well, S is just adjacent to one of the A's, whereas in this one here, S is between both A's. And so the given side is adjacent to both angles. To both angles. And then the authors got a little funny and they called it an angle side side, whereas these are also known as a side side angle, but they even had a little footnote saying more reputable textbooks will call these SSAs and not ASS. Me too. I just think it's, yeah, it's funny. So now we've just got one angle and two sides, right? But from how these are arranged, right, regardless of if you use ASS or SSA, the angle is only adjacent to one of the sides, right? And so given the measure of just one of the angles, along with the length, oh, wow, I combined those, along with the length of two sides, only one of which is adjacent to the given angle, only one of which is adjacent to the given angle. In the case where we're given two sides and one angle, right, so the angle side side case, there are situations where this triangle doesn't exist, right, because one of the sides might be too short or too long or whatever. And so in the ASS case, we can summarize triangle behavior as seen in theorem 12.2, which I'll steal now. We're going to talk about these briefly. You'll know when the triangle you're working on doesn't exist, because you're going to be like, well, what? This side is way too short to be able to handle that angle, for example. Okay. But just as a rule, and because this only applies to the angle side side case, right, these are pretty special case scenarios. But if we let H be C sine alpha, right, then we can talk about A, which is the side opposite alpha. If A is less than H, then no triangle exists which satisfies the given criteria. If A is equal to H, then gamma is 90 degrees. So exactly one right triangle exists which satisfies the criteria, right? Just brings us back to a right triangle. If A is between H and C, then two distinct triangles exist which satisfy the given criteria. And then finally, if A is greater than or equal to C, then gamma is acute and exactly one triangle exists which satisfies the given criteria. And so now you've seen it, right? But like I said, if you come across a triangle that doesn't exist, you'll know, right? Because things just won't work out. Okay? So we're not really going to use theorem 12.2 at all. It's just good to have. We can calculate the area of a triangle using theorem 12.3. This we will use. We can calculate the area of a triangle by using theorem 12.3. Theorem 12.3 says that suppose we've got all these angle side opposite pairs, then the area A enclosed by the triangle is given by, well, we've got three formulas that are equivalent, right? So depending on what information you have, right, whether it's B, C, and alpha, A, C, and beta, or A, B, and gamma, right? Depending on which information you have, you'll be able to solve for the area. Remembering that you want to use as many of the given pieces of information that you have, right? And so what you'll do is you'll just kind of go through all three of these and figure out how many were given in the problem, and then pick the formula that uses the most of the given values. So, nothing crazy. As an example, find the area of the triangle from the previous example. Right? Find the area of the triangle from the previous example. Bless you. So we were given, the information that we were given was that alpha is 120, A was 7, and beta was 45 degrees. And then we solved that gamma is 15 degrees, B was approximately 5.72, and C was approximately 2.09. And like I said, ideally we would use the exact answers, but because they were so nasty, I'm gonna just use the approximations. So out of these formulas for the area, right, you want to pick the one that has the most given information, the most, right? Some of these we'll have to pull from. It's going to be pretty rare that you have a situation where you don't have to use one that you've calculated, but let's just write out those formulas. So A is 1/2 BC sine alpha, which is the same as 1/2 AC sine beta, which is the same as 1/2 AB sine gamma. For this first one, right, we're going to count how many given pieces of information it uses. I only see alpha because we're given alpha, but then we calculated B and C, right? And so here we have one given. For the next one, we were given A, we calculated C, and then we were given B. So here we have two given. And then finally, we were given A, we calculated B, and we calculated gamma. And so this is just one given. So we use A is 1/2 AC sine beta. So now our area is 1/2. A was 7, we knew that. And here C is 2.09 roughly, right? We should use the, what is it, -7√6, whatever, right? Or even if you just wanted to use 7 sine 15 over sine 120, maybe that's easier, right? That would be your exact answer. But I'm just going to use 209 or 2.09 times the sine of 45. Right. I'll just make a note here that we should use the exact value (7 sine 15 over the sine of 120). But I can't remember what I did in my Martha Stewart notes here. So I've just got A as approximately 5.17. It'll be slightly different depending on if you use 2.09 or the exact answer. Can I borrow your calculator? Thanks. All right. 7 times 2.09 times the sine of 45. Oops, did not like that. Sine of 45, growing pains, times 2.09 times 7 divided by 2. Looks like I use the approximation, which is fine, because that's what I wrote. Thank you. Okay, so now we found the area I wanted to do. Oh, so take it away. All right. Any questions about that one?
We want to use the one that has two givens, but then since we already solved for it, we can use the 2.09.
Yeah, so we want to use the one with the most givens, so that's why we use the middle one. But we solved for C, so that's the one that we have to use. Right. So, because we need 3 pieces, but 2 were given, so that's better than 1. Right. Okay. Have you guys had to talk about bearings? Never eat shredded wheat, northeast, southwest. I don't know. What do you guys have for? I always just use never eat shredded wheat. Northeast, southwest. Yeah. Maybe you just have them committed to memory. I guess it's not that hard. Oh yeah, they're all multiplied. It's just my brackets got lost in the circle. Bearings. Or I guess I should, bearing, singular, is the direction you're heading according to a compass, right? So if you've got a compass now, right, and if you've had a glance at assignment 9, right, there's a lot of kind of compass. So you walk this way and then you walk this way, and what's the distance between these 2 points, right? And so kind of fun problem solving. So a bearing is the direction you are heading according to a compass. Heading according to a compass. Okay. So a bearing is given as an acute angle of rotation to the east or to the west. Got those right, my direction at least, away from the north or south line of the compass. The compass rose, I guess it's called. Beautiful. A bearing is given as an acute angle of rotation to the east or to the west, away from the north-south line of a compass rose. So here, let's see if I can draw. This looks a lot like our coordinate system, right? X and a Y axis, right? And we'll treat them as such. We've got north, south, never eat shredded wheat. There. Okay. If you're heading exactly north, east, south, or west, you say you're headed due north, due east, due south, or due west. What was that TV show? The due south? Can't remember. He was a Mountie, right? Yeah. Anyways, so if we are heading, if we're heading exactly north, for example, we say we are going due north. Right. Due east, due south, due west. Hmm? For example, if we have a bearing that's n 40 degrees E, we actually read this as 40 degrees east, nice, of north. So in terms of our bearings, we know that we've got north here, we've got east here. And so what 40 degrees east of north is saying is that we've got this angle here is 40 degrees, right? And so this side would be at 40 degrees, oh, sorry, north. 40 degrees east of north, which I actually have a hard time because I just read north 40 degrees east, but that's fine. As long as you understand what it's communicating, that's fine. What does that mean? Well, we know that the angle between, right, this is essentially our terminal side, right, is going to be 50 degrees. Yeah.
Wind is always given in the direction it's coming from.
Oof.
So
No, that's.
so we don't have an eastern wind, we have a wind blowing from the west.
Oof. No, I don't like that at all. I don't like that one bit. All right.
Whatever. And you should. It's never started.
Let's do an example, see this in action. Example 12.1.4 is on your handout because it was a long one. Oh, I guess I've got that in my notes. See handout. That's for you guys. I need this one. Not my doing, I just steal them from the textbook, but I do think they're really cute. Yeah, I think there's like HMS Bigfoot or something. Yeah. OSS Bigfoot. Yeah. Yeah. Okay, so we've got Sasquatch Island lies off the coast of Ipizuti Lake. Ipizuti was the fish that we had to find the pH for. Fake fish, unfortunately. I'm sure it's from some show that I've never heard of. Right? You don't just make this stuff up, right? You can't. Although Google only led me to this textbook, so maybe they did.
First thing that comes up.
From the textbook, right? I know, right? Yeah. Yeah. So, I mean, maybe Google some stuff when you're doing the assignment. I don't know. Get creative. Yeah. Yeah. So Sasquatch Island lies off the coast of Ipizuti Lake. As illustrated below, from a point P on the shore, so we've got the shore is basically our x-axis. The bearing to Sasquatch Island is observed to be 60 degrees east of north. Right? Yeah, east of north. Is that what I said? Yeah. From a point Q, that's 5 miles due east, so directly east of P, the bearing to the island is observed to be 45 degrees east of north. So these things change. Assuming the coastline continues to run due east, find the distance from the point Q to the island, right? And so the first thing that we're going to solve for is, well, we just want to know what this distance is. What point on the shore is closest to the island? And so here, if we imagine, right, we know from our triangles that the hypotenuse is always longer than the side, right? Than the adjacent, I guess. And so this distance, well, first we want to know what this point is, and then we want to know what this distance is. Just got question marks all over the place. So what point on the shore is closest to the island? I'll put that in pink. And then how far is the island from this point? Oh, that was a nasty curly bracket. And then just kind of break up what we have to do here. Okay, you'll see from those questions that I gave you, right, it doesn't give you the illustration, you have to make it. And so that's why I want you to work together so you can kind of talk about and decide together what it looks like.
Where is the actual island?
Yeah, this is the island here. It's just the star. Yeah. Okay. We can find the distance from Q to the island, right? If we just focus on the triangle between the PQ, let's call this S triangle. So if we've got, it looks something like, well, put this more on an incline. So now we've got P, not B, P, Q, and S. We know that this distance here is 5 miles. We also know that, okay, well, between north and east, right, due north and due east, we've got 90 degrees, and so 60 of that, and so we've got 30 degrees in the actual triangle that we're interested in, right? And so we know that we have, let's call this alpha is 30 degrees. Should have made this guy bigger. I'm gonna run out of room. So now, the length of the side opposite that is going to be A, right? Arbitrarily naming our angles alpha, beta, gamma, and our sides A, B, C accordingly. And so I'll let this angle on the Sasquatch Island side be beta, which we don't know what it is yet, but we know that we know that B is 5, right? Because it's opposite beta. And then this gamma here, we know gamma because we know that the angle here, gamma is going to be this angle, I guess, this one here. And so we've got 45 plus 90, or if you wanted to, 180 minus 45, end up at the same thing. And so gamma is, let's do 180 minus 45, which is 135 degrees.
Would you consider that given? I mean, it's not like we didn't use like the science stuff for anything, right? Like it's a simple.
Yeah, I mean, it's technically not given, but for the angles, because we're so sure of them adding up to 180, I mean, if I had to rely on some unknown information, I would go for the angles, right? Not the sides. So not technically given, but it'd be my go-to if I had to pick one. Yeah, because it's the safest, right? Gamma and beta are going to be pretty solid. And so beta then is going to be 180 minus 30 degrees minus 135 degrees, 15 degrees. Okay. So we want to find A. So if we want to find A, well, using our sine laws, right, we know, okay, well, we know alpha, I know B. Those are the only things that are technically given to us, right? And so I'm going to use the sine of alpha over A. Can I? Is the sine of beta over 5. I can't. Sine of alpha over A is the sine of beta over B. Here, we're kind of treating beta as if it is given. We know what it is, and so the angles we can kind of
No, not given.
know. Yeah. So we've got the sine of 30 degrees over A, which we're trying to solve for, is the sine of 15 over 5. So A, if we rearrange this, right, is going to be 5 times sine 30 over the sine of 15. Do you want me to show it one more time? No. It's magic.
We need exact.
We'll use an approximation. Yeah. So I find that that is my approximate, or sorry, my exact answer, because I don't think it gives me anything nice. 5 times the sine of 30 divided by the sine of 15. Oh, it does, but okay, here we go. But for our calculations, let's just use the approximation. Let's use 2 decimal places, so to hundredths. 5 root 6 plus 5 root 2 all over 2.
Can you not just do 5 root 8 over 2? Is that different?
Pull out a 5 root 6 plus root 2 is not
Like 10,
root
they're both
8.
5 on the outside, you can just add the 2 roots. So like 5 plus root 6 plus root 2.
No, doesn't the base have to be the same?
Yeah.
Square root at it?
It's like what,
Or no,
like
it's
7
not.
roots?
Because root 6 plus root 2 is not the same as root 6 plus root or plus 2. So,
Root six.
because what you would do, you would pull out that common 5, right? And so if you try the root of 6 and then plus, or sorry, you have to step out of that, plus the root of 2, that's 3.86-ish. And then the root of 8 is 2.82-ish. Or 2.83, I guess, with rounding. So they're not the same. And yes, it has to do with the base. Because you'd have 6 to the power of 1/2 plus 2 to the power of 1/2. Can't do it. But fun to try. Okay, 5 times the sine of 30, because I lost it, divided by the sine of 15 is approximately 9.66 miles. Okay, so now we want to find the point closest, the point on the shore closest to the island, right? And so if we call this point, I don't know, what do you want to call it? Great. Works for me. Now we've got a new triangle, right? QSC or CSQ if you want, or
It's a right angle.
SCQ. It is our beloved right triangles. So now we can find the point on the shore closest to the island. The point on the shore closest to the island. Which is going to look like this. We've got Q here, we've got Sasquatch Island over here, and C here. As you guys already noticed, that's a 90-degree angle, so it's a right angle. And we'll call this angle up here by Sasquatch Island, we'll call it beta again. Except it's going to be a different beta, right? Not the same beta. And we know that this is 45 degrees. Because because they have to add to 90 degrees. So I guess we weren't given that, but it's known. We said that this side, C, is roughly 9.66 miles. And I guess we'll call this B is some unknown miles. Keeping track that now you've erased your memory from all your alpha, beta, gammas, ABCs. We're starting fresh with new ones, new triangle, right? And so they're not necessarily going to translate. And so we'll let alpha be 45 degrees, which means this is A, which is what we're going to solve for next, right? But first we're going to solve for B, because we want to know what is the distance, or sorry, what point on the shore is closest to the island?
But we already found that it's called C, right? Is that not
Well, we want to know how far away that is, probably from Q.
Okay.
P or Q, it doesn't matter. It's not clear though from the question, I guess. But it is point C, but we want to find what point C is. And so, well, now we've got this beautiful right triangle. So now we can use our SOHCAHTOA. And if we're solving for B, the length B, well, we know that beta, must be, well, technically 180 minus 90 minus 45, right? Which is going to be 45 degrees. So then, if we know the hypotenuse, right? That's 9.66, so we're going to use that. And we're trying to solve for B, and we know we just solved for beta. So we've got opposite over hypotenuse, or let's use the 45 from alpha. Let's use that. We know that adjacent over hypotenuse, so SOHCAHTOA, the cos of alpha is adjacent over hypotenuse. It's been a while. I keep having to SOHCAHTOA. So the cos of 45 degrees has to be B, which we're solving for, over C, and I'm just going to use the approximation 9.66. 9.66 times the cos of 45, B is roughly equal to 6.83. So therefore, the point on the shore closest to S is 6.83 miles from the point Q, which was 5 miles from the point P, but I'll just leave it at that. So now, the last thing we wanted to do was how far is the island from this point, right, the closest point. And so now we can just find the length of A. We got this right angle. So finally, we find the distance from C to S. We've got the opposite, and we know the hypotenuse of alpha, and so we can use sine of 45 degrees is A over 9.66. And so, oops, y. A is approximately equal to 6.83.
Sure.
You
Angles are the same, but the sides are gonna be the same.
Yeah. So A and B are equal, right, because the angles are equal. And so, as expected by symmetry, any questions, comments, concerns? Looking forward to the law of cosines next day. That's almost a week until then, I guess. Until then, you've got plenty of assignments to keep you happy. All right, no questions?
I have a quick question.
Sure.
On the assignment 9, question 2,
Uh-huh.
do you mind trying to draw that for us? That feel like it's a bit long.
One. Okay.
The real part about variance is you can totally be in a completely different quadrant and still say 220 degrees east of north. It's unnecessary, but you totally could. If that's where you're
Let's see.
Right? You become low, that's not. Yeah.
In my mind, it worked out because it's going to be like the flare, and then you've got one here and one down here. That's why you're working in groups, so you can talk it out.
So we're like 2 different flare locations, or is it the same?
There's one flare. Right, so sees a signal flare, and so
I have 2 different.
from her location. Let's see here.
Because I thought maybe if it was north 15 degrees east, that makes a lot more sense than 150. Because I have.
Well, the only reason that I'm pretty sure of the 115 is because I reacted because it's more than the 90.
Yeah. So if you southeast of that.
Okay, let's just put the flare somewhere in the center, right? So then we can kind of work around it. I want you to do it in groups.
So we're one big group right now.
Yeah.
I know, but I'm part of it. That's not the idea. Okay, so the flare, yeah. So separately, she's going, so pointing north, and then 115 degrees east of north. Okay, so she must be up here somewhere. Right, and so here, this must be Bigfoot, right? Because she's going north, and then we've got 115 degrees. Let's say like that. Right?
Because then the other shape is northeast. No, like there's the.
So then.
They see another one that shows that the flare is northwest.
So then, okay, so from this, I think it's from his position. Sorry, guys. The captain of the Sasquatch finds the signal flare to be at a bearing of 75. So that's going to be pointing up, right? So he must be somewhere down here.
Yeah.
So north.
And then it moves 5.
And then, so let's say just kind of arbitrarily drawing it here.
I don't know why that doesn't.
75 degrees, right? The SS Bigfoot is 5 miles from the Sasquatch. This is S. And the bearing from the Bigfoot.
From Bigfoot?
And the HMS.
Maybe I'm reading it wrong. I'm just kidding.
I think I typed these too fast.
This is from Bigfoot.
Mm-hmm.
Sasquatch or MS of Sasquatch is north 50 degrees east, so it should be north But that boat we just found is northeast of the flare. So don't
Where
make
does that
sense.
make it? Yeah, it says that they have.
And the
same
bearing from
bearing.
the Bigfoot, so from up here
Yeah, which means
to
the
here.
Bigfoot would be higher than the.
So here's my Bigfoot. Here's the image
Yeah.
Sasquatch. That's the 5.
Okay.
And then if we do the north 75 west,
Yeah.
it's somewhere around here. And if you do 15 degrees instead of like 115, it would make
But I'm
more. It would make
pretty
a
sure they're
triangle.
going to be like this, right? And then, so if we say that this distance here is going to be 5 miles like this. And the bearing from the Bigfoot to the Sasquatch, let's say.
It's confusing.
Yeah. I think it should say to the Sasquatch is 50 degrees east of north.
Yeah, so it would be
Yeah.
Wait, so the Bigfoot's.
Mm-hmm.
that's why I thought maybe it was a type of, it was north 50 degrees east. And that would make a triangle. It's the only way.
Stay tuned.
Okay, so let's skip to.
There. That'll be there.
For now,
Like center
it's going to
is
be
like-
fine, but I'll just make sure that I typed it correctly. Yeah.
Looking at it, just like maybe I can try to draw
Mhm.
it. I'll say I can draw it.
Because then from here, right, we've got, so from the Bigfoot,
We could leave this as a class game.
Please don't tell anybody.
yeah, just that I'm recording though, so. Well, I feel like,
Just so it's clear.
yeah,
Neither of these ships are setting the flare, right? The
no,
flare is
it's
separate.
just a flare,
Okay.
yeah. Mhm.
There's two locations somewhere.
Let me map it out.
Expect an email.
No, I'll just tell you guys on Tuesday.
That's fine. Just-
Yeah, let me map it out and just make sure that it makes sense. It was just me trying to be a hero, getting you guys your last assignment. That's what I get. Oh, wow. Anyways, so don't worry about question 2, but you can do question 1 and some of question 5. And probably if you just look at the handout, all of them. So anyways, all right, I'll work on this one. Any other questions? No. See you guys later. Bye, guys.